Hey everyone, welcome back, and today let's solve Leetcode problem 3195 titled Find the Minimum Area to Cover All Ones, Part 1. So we're given a 2D binary array grid, and we need to find a rectangle with horizontal and vertical sides with the smallest area such that all the ones in the grid lie inside that rectangle, right? And we need to return the minimum possible area of that rectangle while still covering all the ones in our input grid. So in example 1, they also give us an image to better visualize how our input matrix or grid, if you will, would really look like. In this case, it has 2 rows and 3 columns, and we have ones on this index, this square, and this square as well. In this case, there isn't actually a sub-matrix, or rather square as a sub-matrix that we can actually make to cover all 3 of these ones because of how they're placed in the matrix, and so we'd have to actually use the entire matrix itself, which is, of course, the worst case scenario, which in this case would have an output of 6, or the total area of the entire input matrix, right? In example 2, however, since we only have 1, we can just use the index or square of that singular cell that is a 1, right? And so we would just have an output of 1 because the area of a single cell is always just going to be 1, as these are unit cells, if you will, right? So for the constraints here, we see that the number of rows and columns in our grid are always going to be between 1 and 100. Any value in the grid is guaranteed to be binary, 0 or 1, and there is going to be at least 1 in the grid for every input. And so kind of just confirming what the problem statement said and guaranteeing that we do have valid inputs, which brings us to the main observations that we really need to make to solve this problem in the most efficient way possible, right? And that really is that really the minimum area rectangle we can determine strictly by the minimum and maximum row and column indices that actually do contain a 1, kind of like yesterday's threshold problem or limiting problem, if you will, where we're trying to find the extreme points of, in this case, the index of the minimum and maximum row and column indices that contain a 1, right? And we don't need any, extra fancy data structures to store those values. It's just our straightforward simple lists, right? Or in this case, I should say integers, right? And the 4 variables that we're going to use to actually track those 4 boundaries, if you will, would be a minimum row and a minimum column variable. And quite intuitively, that's going to be the smallest row and column indices, where we'd see a 1, and a maximum row and maximum column variable, which would be the largest row and column indices, where we'd see a 1, and try to form the bounds of our grid to minimize its area as we actually do that, as we iterate over our input matrix grid, right? So really no need to use any extra data structures here. We can actually solve this just using extra variables and integers to kind of optimize our memory efficiency and memory time complexity, right? So that brings us to the high level kind of rundown of how we're going to solve the problem. Effectively, we just iterate over every cell in the grid after initializing our minimum row, minimum column, and the maximum row, maximum column variables, and then we simply update them for whenever we see a 1 in the grid by minimizing the minimum row and column for their corresponding indices and maximizing the maximum row and column for their corresponding indices. And after we actually scan the input matrix, the height of the rectangle would be kind of calculated with a formula here that we predetermined as the maximum row minus the minimum row plus 1 as the height, and the width of the rectangle would be the maximum column minus the minimum column plus 1. We simply multiply those 2 values because that's the definition of the area of our rectangle, and that would give us the smallest area of our rectangle because we're just covering the bounds of the cells that contain 1s for that rectangle, right? And kind of going back to example 2 here, we could as well have outputted 4. That's technically valid because 4, the entire arrays, the area of the entire input matrix still does cover this 1, but the extra 3 are redundant. The extra 3 cells are redundant because we don't need to include them, as none of them are 1s, hence none of them are really important, and so the bound, if you will, of our rectangle would just be the singular cell or index for both our row and column, and hence it would simply just be 1, right? Because that calculation or multiplication value of max row minus min row plus 1 and max column minus min column plus 1 would simply just be 0 plus 1 times 0 plus 1, or 1 times 1, which we know is simply 1. So we're cleverly using the bounds of our rectangle to limit how much space we actually need to cover all the ones in the input matrix, to avoid using any extra cells to make our value higher than it really should be. Because at the end of the day, we're still trying to minimize our output to still cover all of the ones, right? We want the smallest area of the sub-rectangle, or the sub-matrix, if you will, right? So now let's actually get into the code here. Technically, if this weren't a Leetcode editor and all our packages and libraries weren't already imported in our Leetcode code editor, we'd have to technically import math. I'm not doing this for the sake of today's video because it is already imported, pre-imported in Leetcode code editor, but really we're just using this math module, I should say, to use math.inf for our initial values. That just helps us set up our infinite boundaries for our actual minimum column, minimum row, maximum column, maximum row variables, but we don't really need to do that in Leetcode specifically, right? So now let's actually initialize the 4 variables that we did discuss before. First one that we discussed was the minimum row. Again, the order does not really matter here. Sorry, I have all caps on. I'm just going to call it minimum row, and it's going to be math.inf. What inf means is really just infinity, right? We're initializing minimum row to positive infinity, and any actual row index that we actually see from 0 to length of grid minus 1 has to be, of course, smaller than infinity, so it will update correctly, right? We'll also get a minimum column with the same logic here, still going to be infinity as we're trying to minimize the value, and so we're guaranteed to see smaller values the moment we start iterating over the grid, and so we're going to update that accordingly as well. But the whole point of minimum column is to just store or catch the smallest column index that does have to contain a 1 for that boundary point. Now, very similarly, but for the kind of opposite logic, if you will, for the maximum row and maximum column here, maximum row is going to be math.negative infinity, or in this case, the way it'd be phrased in Python is math.infinity, and we tag on a negative to it, which would represent negative infinity, right? And that would basically just be any encountered row index to be larger than math.infinity. Negative infinity, I should say, and we'd update that accordingly. And maximum column, again, very similar logic, is the same exact thing. This is simply just going to store the largest column index, and it's going to start at negative infinity to ensure that we always encounter values greater than it, right? So once we actually start with that, or once we actually initialize those 4 integers, now we can actually start iterating over or processing our matrix. And we do this with very standard double for loops here, or nested loops, I should say, for every r and row. And the reason why I'm getting 2 iterators here is because I'm actually going to enumerate over the grid to also keep track of the index along with the value, because we care about both of those kind of integers, if you will. So for every r and row in the enumerate of our grid, right, effectively we're just starting to first scan the rows in our outer loop here, which is what this is. So r is going to give us the index or the row number, and row is actually going to give us the r value alongside each row, right? Basically, enumerate just helps us track both the row value and its index kind of concurrently in a very neat matter on the same line, right? And for our inner loop here, we're going to do the same thing, but in this case for every column index. And so for every c, in this case is what I'll call it, and value, still using enumerating, or still enumerating over it, for each row to get the number of columns, right? That's going to give us the column index c for every column, right? Or rather for every row to get the number of columns, where we're basically just systematically inspecting every cell in the input grid. Now, for every kind of iteration of these nested for loops here, if the value is actually equal to 1, only then do we actually care about this, right? This is kind of like the key moment of our solution, because if we find a 1, that's a possible boundary candidate, if you will, right? Because every time we run into a 1, we refine our rectangles edges and update our boundaries accordingly that we store in these variables here on lines 3 through 6. And the way we would kind of initialize that is first we'd refine minimum row. That's going to be, of course, you guessed it, the minimum of itself, because we don't want to make it larger, and the current row index, right? So if the current row index that we store in R is smaller than the previously stored minimum row, we'd have to replace it, which would just potentially move the rectangle's top boundary upward. Now, with the very similar logic here, we're going to update minimum column, still minimizing it. In this case, it's going to be the minimum of itself, or C. Why itself? Well, because we don't want to make it larger, and C, because that's going to give us the actual column index, right? That's going to basically potentially move the left boundary even more leftward to see if the current value is an actual 1. Now, kind of opposite logic again, if you will, for the maximum variables. Maximum row, in this case, we're going to be trying to maximize it of either itself because we don't want to make it smaller, and R again. Why? Because we have to actually push the bottom boundary down anytime we find a 1 in a lower row, and very similar logic, maximum column, so the maximum of itself, or, you guessed it, C. We're pushing the right boundary rightward when we actually encounter a 1 in a new column on a righter column. Right? That is the main observation here. Now, another very important observation that we can make is if we don't see any 1s, of course the result would just have to be 0, right? What if there are 0 1s or no 1s at all in the matrix? We technically still do have to handle that condition, because if minimum row is still infinity, we know that there is actually 0 1s. And so how would we actually, efficiently check if minimum row is equal to infinity, meaning we never actually updated that? Well, it would be once we actually exit the loop. So once we actually process all the cells, and if our minimum row value stays the same, meaning it's still math.infinity or just infinity, we know for a fact, or again checking that condition, if we never updated minimum row, we know for a fact there were no 1s, and so our area has to be 0. So how would we potentially output that area of 0? Well, we'd return 0. And that's really it, right? Now, what if we don't enter this conditional? What if we don't return 0 because we did actually find at least a single 1 in our matrix? Well, then here's where we have to actually calculate the height and width of our bounded rectangle that still has that minimum area. And once we calculate those two values, width and height, we simply return the product of those two values to get the actual final rectangle area. That's still minimized area bounded by our minimum row, minimum column, maximum row, and maximum column variables. So how would we calculate height? We briefly discussed it in the high-level explanation. It would be the maximum row minus the minimum row and plus 1 to account for that 0 index offset to actually get that accurate window length for the height, right? And very similarly, the width would be the maximum column minus the minimum column, and still doing a plus 1 to account for that 1 offset, right? And once we actually compute the both width and height, then we have to actually include both endpoints, and that's why we're adding 1, right? So in this case, if minimum row is equal to maximum row, that's still technically a height of 1, and so even though we get 0 for that subtraction operation, we'd have to add 1 to account for that. That's why we're adding 1, to kind of reiterate. Now, effectively, all we have to do is return the product of these two variables, so height times width. Why? Because that would actually give us the final rectangle area and complete our logic fully. So in this case, if we kind of go back to example 2 here, or rather 1 here, we'd see that our maximum row would still be this guy right here. Why? Because we do actually see a 1 in every single row. Very similarly, we do also see a 1 in every single column. And so both maximum row and maximum column would be maximized to the number of rows and columns in our matrix. And so in that case, it would really just be the height times width being 3 times 2, or basically just 6. That's kind of just a brief example and demonstration of how that would work in terms of example 1. Right, so unless I made any syntax errors here, should be accepted, and there should be a valid solution. Okay, let's go ahead and see what math error. I don't know what exactly. Okay, yeah. So I forgot an equal sign. I'm doing a comparison operation. I have to have 2 equal signs. Sorry about that. But now, if I were to submit this, as you can see, this does get accepted, and this is just about as efficient as you can get it to be. Right, so quick summary. How did we really solve this problem, right? How did it work? Well, effectively, as soon as we found a 1 as we scanned our matrix, that would kind of help define or refine our boundary points and scan the input matrix row by row, updating those minimum and maximum row and column indices accordingly. And we had a quick edge case in the sense that if we didn't see any 1s, we'd have to return 0. And we could check for that if we never updated our minimum row variable. And the height would be calculated as maximum row minus minimum row plus 1, the width as maximum column minus minimum column plus 1, and effectively just multiply those two values for the area, right? And that's going to be the minimal rectangle area that encloses all of the 1s without using any extra redundant space, right? So that brings us to the complexities of this solution here. So for the runtime complexity, it really is pretty straightforward. Big O of m times n, and the number of rows and the number of columns. Why? Well, because we really just use two nested loops here to go through every row and column, or every cell exactly once in our input matrix here. And in each iteration, as we actually visit each cell exactly once, we're just doing some constant time work and operations per cell, which won't actually affect our runtime complexity. So our runtime complexity is big O of m times n, or mn. And as we briefly discussed in the high-level rundown, the memory or space complexity is actually constant because we're not actually using any extra fancy data structures. We're just using these 4 integer variables, max, minimum, and row and column, right, to kind of just store the 4 boundary variables and a couple of height and width calculations, but that's still constant regardless of our grid size, right? And so it is a big O of 1, or constant memory or space complexity. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye. Thank you.